Kia ora koutou, no mai, haere mai. Welcome to lesson 23 for introductory physics. This is the second lesson of the thermal physics section, which is just 3 lessons long, and it'll continue with some of the topics we've already met, but there will be 2 focuses. One is on thermal expansion and the other is on heat transfer. So we introduced heat and we defined it in lesson 22, but now we're going to look at how it actually occurs in different types of substances. So the goals are to look at thermal expansion and understand why it occurs, but also calculate how much thermal expansion we expect in different materials given different temperature changes. So there will be an equation and some calculation to do there. We want to look a little bit more closely at water as it approaches its freezing point, because it is a fairly atypical substance as it changes from a liquid to a solid. So we're going to investigate that. And then, as I said, we want to look at heat transfer. So we already defined heat. Heat is the flow of energy between objects, energy moving from one object into another object and increasing its temperature. Well, not always increasing its temperature, as we'll see, but often increasing its temperature. We want to look at how it does that. Finally, we're going to meet Newton's law of cooling, which is a very brief topic, and we're going to describe the vacuum flask and talk about how it overcomes each of those 3 types of heat transfer that we'll meet in that part of the lesson. So the first thing we're going to do is look at heat expansion or thermal expansion, things expanding as heat is supplied to them or as they increase in temperature. We already met the idea of atoms being in a solid and being bonded to their neighbours, so they're all stuck in place. They've got these bonds between their neighbours, and they can't move. They jiggle a bit, as we said, but they can't actually move outside some little region unless they get warm enough to break those bonds and become a liquid. But while it's still a solid, they're stuck in their own little space, their little pocket within the solid. However, as they get more jiggly, they start bouncing towards all their neighbours. So this is before the bonds break, before it becomes a liquid. While it's still a solid, as the atoms get a bit more kinetic energy, get a bit more temperature, their temperature increases, and all its neighbours are doing the same thing. They're all bouncing around, they're all trying to be a bit more energetic, but they're all still cooped up in their own little location because of all those bonds that are still there, they haven't yet been broken. If all of the atoms are doing that, then they all just sort of want to push apart a little bit. They all want a little bit more space to do that jiggling in, that vibrating. They want to be able to bounce around in a little bit bigger space. And if they all do that, if they all spread out, then overall, the solid is going to get bigger. It's going to get bigger as a whole, so that every atom now has a little bit more volume, a little bit more space in which it can vibrate, in which it can jiggle around in. And so that's all that temperature expansion is, thermal expansion. It's just the result of all of the atoms in the solid wanting to bounce around a little bit more. Not wanting to, they do bounce around a little bit more. That's what being hotter means. Hotter means more linear kinetic energy, or translational kinetic energy. And so if they've all got a bit more of this translational kinetic energy and they're all moving around a bit more, then overall the solid has to get a little bit bigger to allow that, in order to facilitate that extra jiggliness. So that's what happens, and solids get bigger as they get hotter. We're all usually aware of thermal expansion as something that occurs. Even if we haven't seen it directly, we're often aware of that as a phenomenon. So that's all that's going on. The atoms jiggle a bit more, they need a bit more space, so the whole solid gets a bit bigger. The same thing happens to liquids. Remember that liquids aren't bonded to their exact neighbours, but they are all flowing around. And if they're all getting a bit faster and a bit more energy as they move, and they're pushing other ones out of the way a bit more, then they will all end up just with a bit more space between them. So liquids do also experience thermal expansion. For gases, as we've talked about, gases fill their entire container. So it doesn't really make sense to talk about expansion of a gas, because the gases will automatically expand to fill any container that they're placed into. So it does get more complicated when you start to think about the effect of thermal expansion on a gas. It's not straightforward, and we're not going to bother looking at it in this case, but we have talked about the idea of pressure changes with volume for a gas already, and as you would expect, temperature changes are going to result in pressure changes as well. Since the amount of space that the atoms in a solid need is going to be determined by the solid itself, by what the solid is made of, it makes sense that the amount the solid expands with a change in temperature would depend on what the solid is made of. And indeed, that is the case. different materials will expand different amounts with the same change in temperature. So if you have two 1 meter long bars of two different materials and you heat them both up the same amount, maybe increase both of their temperatures by 20 degrees Celsius, then you potentially would see different changes in lengths for those two bars if they are made of different materials. The linear expansion coefficient is the number that tells us how much that length is going to change. For each type of material, we have to go and figure out that thermal expansion coefficient, and scientists have already done all the work for us, so we don't personally have to figure it out. We can just look up the values in reference tables. So that thermal expansion coefficient, which we write with the symbol alpha, just tells us how much the material expands. It's a ratio of the new total length versus the original length, essentially. We'll look at the formula in a moment. But the higher that coefficient is, the more the material will expand. So something with a bigger alpha is going to expand more than something with a smaller alpha. So this slide and the next couple are not in the textbook. I think they may be in a little extra section at the end of the chapter, but they're not in the main content of the textbook if you are following along with the textbook. So if you know how long an object is and the linear expansion coefficient, then you can get the change in length pretty easily. It is just the original length times that alpha, the linear expansion coefficient, times that change in temperature. That is all that the change in length is. So delta L, remember delta is change in, delta L equals L naught times alpha times delta T. The units for the linear expansion coefficient you should be able to see from the formula. So I'm going to go back a slide again, sorry. Go back a slide, we can see on the left side we've just got a length. So that could be any units, but we're thinking dimensions at the moment. Dimensions is it's a length. And on the right hand side we've got L naught, which is also a length. But then we've got alpha, which we don't know yet, and delta T, which we know is a temperature. So in order for the dimensions to balance in this equation, we've got a length on both sides, so that's fine. But we've got a temperature on this side, and we don't want a temperature because there's no temperature on the left side, so the alpha dimension must cancel that temperature dimension, so alpha must be temperature to the -1, or 1 over temperature dimensions, and indeed that's exactly what it is. So it's either Kelvin to the -1 or Celsius to the -1, depending on what your temperature measurement is in. But remember that Kelvin and Celsius, if we're talking about a change in temperature, which is what we're talking about for linear expansion, Kelvin and Celsius are going to be the same value anyway, so it doesn't actually matter which of these values you use. Some examples of these linear expansion coefficients. We have aluminium at 25 times 10 to the -6 per kelvins. Copper alpha is 17 times 10 to the -6 per kelvins. Glass about 9 times 10 to the -6 per kelvins, and concrete about 12 times 10 to the -6 per kelvins. Glass and concrete are both about because the exact thermal expansion coefficient will vary depending on the exact makeup of the glass and concrete. You can create them differently. You can change the ratios of different elements in the glass and the concrete, and that will change the resulting substance and therefore change its linear expansion coefficient. But they are usually in those regions given. As an example, because this isn't in the textbook, I have included an example here in the lecture notes. Let's say we have a rod of aluminium and a rod of concrete. Both are 1 meter long. How much longer will they each be if they are heated up from 20 to 100 degrees Celsius? And we've got the linear expansion coefficients on the previous slide. So I will do this on the document camera, even though it's very straightforward. So we'll jump over to that. So first thing we want to do is we said that we are looking at aluminium and concrete. So we need aluminium, so Al, we'll need alpha for that. And we'll need concrete, we'll need alpha for that. So for aluminium, we have 25 times 10 to the -6 per kelvins. And for concrete, we have about 12. I'm just going to use 12 because I don't have any information to change it. 12 times 10 to the -6 per kelvins. So those are our two linear expansion coefficients. We are told that both rods have an original length of 1 meter. So that's for both concrete and aluminium. Well, it says 1.0 just to give us an extra significant figure. And we're also told that the initial temperature is 20 degrees C. The final temperature is 100 degrees C. And so therefore the change in temperature is equal to 80 degrees C, which is also equal to 80 Kelvin. So you can use either of those. 80 is the same value because we're talking about a temperature difference. Just as a reminder, since this is, as I said, one of the common sticking points, if we were to convert this into Kelvin, then we would have temperature initial being 293 Kelvin, and we would have final temperature as being 373 Kelvin, and we would still get the same change in temperature of 80 Kelvin. So just a reminder, they are going to be the same in Kelvin and Celsius because it is a temperature difference, but the actual specific temperatures will be different. So then we can just calculate our results, and this is a very straightforward formula. As I said, the change in length is equal to the original length times alpha times the change in temperature. So for concrete and for aluminium, we just plug those values in. So delta L for concrete is equal to 1 meter times 12 times 10 to the negative 6 times 80, because we've gone up 80 degrees. So that gives us, if you get your calculators and plug those values in, then you will find, I'm just double checking my result here, we have concrete, we have 0.00096 meters. That 10 to the negative 6 means the changes in length are going to be very small. And that makes sense because we know that things don't suddenly get really big when they get hotter. If something had a huge thermal expansion coefficient, then just on a hot day it could be really big compared to what it was on a cold day. And that's not very common, although there are some materials which get higher coefficients than this. They're still all relatively small. So it's 0.0096 meters, which is, if you want to convert to millimeters, 0.96 millimeters. So heating it up, a block of concrete from 20 degrees Celsius up to 80 degrees Celsius, sorry, 100 degrees Celsius, a change of 80 degrees Celsius, it only gets about a millimeter longer. So our precision would have to be quite high to measure that at all, because we said that the length of the block was 1.0 meters, that initial length, or L0 as we call it in this one. L0 was 1.0 meters. L final is still 1.0 meters. Right? It's still 1.0 meters because our precision is not enough to pick up that change. So if you just cared about the change, you could measure that and it would be about a millimeter. If you cared about the original versus the final length, then in both cases it's still going to be a meter because the change is not big enough to notice. Exactly the same thing for the aluminium. So change in length for aluminium, we just do the same formula. So 1 meter is the original length, but now we've got 25 times 10 to the negative 6, and we've still got 80 degrees Celsius temperature change. And that gives us 0.0020 meters. And again, converting to millimeters, we get 2.0 millimeters. So we have a 2 millimeter change for the aluminium bar. Still not noticeable when we're comparing original and final lengths, but a more substantial change, twice as much as we saw for the concrete. And that makes perfect sense because if we look at the two linear expansion coefficients, alpha for concrete was 12 times 10 to the negative 6, and for aluminium it was 25 times 10 to the negative 6, which is about double. Right? Double would be 24, but it's just slightly above that. So we get slightly above double the expansion. So that all makes perfect sense, but it also hopefully demonstrates that that's a very easy calculation to do. You could also do it back to front the other way. If someone told you how much it expanded, what the original length was, and the change in temperature, you could figure out that expansion coefficient, or you could figure out the change in temperature if you got the other 3 bits of information. Any 3 of those bits of information, you can then figure out the 4th bit. The other thing that we sometimes might get a question relating to is the ratio of that length change. So the change in length as a fraction of its original length as a percentage, in which case you might not need to know the actual original length because you're looking for delta L over L naught. So actually I'll jump back to the document camera just to explain that one a little bit more. I'll get a new sheet. If we know that the change in length is equal to the original length times alpha times the change in temperature, and you want to know how much as a percentage an object changes, that's delta L as a percentage of L naught, how much bigger it gets, So that's just alpha delta t. All we do is divide both sides by L naught, and we get that. So the ratio, the change in length as a fraction of its original length, is just alpha delta t. So if you know alpha and delta t, you can say what percentage the object will change by, even if you don't know that original length. So you may occasionally get questions like that, but generally we'll just stick to fairly simple things. Here's a length, here's a change in temperature, here's a coefficient, what's the new length, things like that. So there's the answer typed into the slide, just as I often do. I worked through on the camera, but you can see it in the slide notes as well. And I'm not sure why that suddenly went through. It's not very happy with that. All right, sorry about that. Here we go, thermal expansion. Thermal expansion can be useful. It's useful in things like thermometers. We rely on thermal expansion. We rely on thermometers expanding with a strict, repeatable amount every time they are heated up by a certain temperature change. So with thermometers, they have liquid mercury or liquid alcohol inside the thermometer. When it's silver, it's mercury. When it's red, it's a liquid alcohol. And thermal expansion, as I said, applies to liquids as well. And so as they get hotter, they expand, and as they expand, they reach further up the tube. And because they always reach the same point at the same temperature, because their expansion is predictable and repeatable, it means that we can calibrate the thermometers. We can say, well, whenever it reaches this exact line, it's always at exactly 30 degrees Celsius, and here is exactly 40, and here is exactly 50, and so on. So it is repeatable and therefore provides a useful measuring device. However, we also get thermal expansion which is not useful, and that is things like thermal expansion of train tracks or just buildings in general. Train tracks are one of the classic ones. During heat waves, you'll see photographs of train tracks. They are nice long rods, and as you saw, the longer an object is, the bigger its change in length is going to be. That 1 meter block of concrete got bigger by 1 millimeter, but if it was 2 meters long, it would have got bigger by 2 millimeters. If it was a kilometer long, it would have got bigger by 1,000 millimeters, right? So that's 10 meters. So a kilometer long block of concrete would get bigger by 10 meters. So you can see that train tracks, which are made of really long, big blocks of steel, or whatever they're made of, I don't even know if they're steel anymore, but whatever they're made of, they still will expand, and the longer they are, the bigger that change in length is going to be, and they only leave little gaps for it to expand into, and then if they try and expand beyond that, this train track is pushing against the next piece of train track, and it can't get any longer, so instead it just starts buckling in the middle to allow that extra length to accommodate that extra length. So sometimes thermal expansion can be very bad. And as I said, that's true in buildings and other structures as well, not just train tracks. So on the left, we see a photograph of a bridge. The bridge can expand as it gets hotter. So what we have is these little tongue and groove joints where the metal prongs can expand into each other. So there's gap left so they can move into each other. And that will allow for the thermal expansion without causing buckling on the bridge. So when they create bridges, they check the environmental temperatures, they check the size of the bridge and how much expansion they can expect even under extreme temperature changes, and then they always allow a little bit extra for safety, and then they create these grooves, these joints to accommodate at least that much expansion, so that if the bridge does get to those extreme temperatures, it still won't cause any structural damage. We see the same thing in buildings. As per the middle photograph, they've cut a strip out of a brick wall to allow for the expansion of the bricks during hot weather. You'll see the same thing on driveways. When you see a freshly poured concrete driveway, the first thing they do is go and cut grooves right through the concrete. And the sole reason for that is to allow for the expansion of that concrete. Remember that we said 1 meter of concrete will expand a millimeter under an 80-degree temperature change, while the change in temperature for normal weather extremes might not be that much. You might easily get an environment where it can go from 0 up to 40, and that's half of that temperature range, so it could expand 0.5 millimeter. So you need to allow space for that concrete to expand 0.5 millimeter, otherwise it will be pressing against itself and it will crack, and so that's why we cut those grooves into concrete. The last picture is actually a the new method for creating train tracks. As I said, they used to just push against each other, and then when they couldn't expand anymore, they would just buckle. Now what they do is they actually do it how it's pictured here, where the end of one train track piece extends alongside the next train track piece, so that if it needs to expand more than you've left room for, it will just do so alongside the next bit of track rather than pushing into it and buckling. Now, it's not perfectly reliable. You can still get buckling in extreme cases, but it's a lot safer. It provides essentially unlimited room for expansion. Really don't know what's going on. I must have left some timings on here, which is why it's jumping forward some slides, but we'll get there. A bimetallic strip is just a nice little invention that was made out of two different metals. I honestly don't know who invented it or when, but what they realized is that if two different materials expand at different rates, different alpha, different linear expansion coefficients, then if you attach them together, you merge them, like fuse them together into one block of metal, then the two sides of the metal will try and expand at different rates. And if one side expands more than the other, then the whole object is going to curve, and that's exactly what we see. The example here, which I believe I've lifted straight out of the textbook, is alpha for steel being 11 times 10 to the negative 6, and brass having an alpha of 17 times 10 to the negative 6. So brass tries to expand more than steel does in the same temperature change, so the brass side is going to be longer than the steel side, and the strip will bend towards the steel so that the steel is curved inwards and is a shorter length than the brass on the outside. These are very useful. They were how all thermostats were controlled for home heating units before the advent of digital temperature measurement and control devices and units. And so what they would have is they'd have these strips, and if the temperature got too high, the strip would curve too much and it would complete a little circuit which would switch off the heating unit. And you could do the same thing with a cooling unit. If it got too straight, then it would complete the circuit and turn on the cooling unit, turn it other way around, turn off the cooling unit. So they used these for actual thermostat regulators. So when you change the dial, you were just changing where the end point was, how far that strip had to curve before it hit the little button that would complete the circuit. So actually a very useful, very practical invention, this little strip of two different metals. The next bit, as I said, is about water and ice. We've talked about thermal expansion, but water is an interesting one because it actually does the opposite as it gets close to 0 degrees Celsius. Liquid water will expand normally above 4 degrees Celsius. From 4 degrees Celsius up, it will expand normally. However, as it gets colder, below 4 degrees Celsius, most things, if they expand when they get hotter, you expect them to get smaller as they get cooler, and that is true for almost everything, but water actually gets bigger as it gets colder. Once it gets down to 4 degrees Celsius, liquid water will start to expand rather than get smaller, and once it reaches its 0 degree state and turns into solid ice, it becomes far less dense than liquid water. And we're all familiar with the idea of ice being less dense than water. Ice floats. That is unique among solids. And that's because of the way the solids form into that. So the liquid water molecules form into the solid water molecules. We've already talked about the idea that solids are just big lattices of atoms and molecules that are all bonded to each other. And the way they do that for solid water, for ice, is to form these nice hexagons. And these hexagons have big empty spaces inside them. For liquid water, because they're not bonded into those hexagons, those liquid water molecules can go anywhere and they actually fill in that space that would be empty for a solid ice block. So water ends up taking up less space than liquid water takes less space than solid water, than ice. So that's why ice is less dense and why it floats. We already saw that something less dense will float. So ice floats on water because it is less dense than water, and it is less dense because the structure of the atoms and molecules in the solid form of water is very spread out, very spaced out compared to how packed in they can get when it is liquid. As ice melts, the bonds between the water molecules break, becoming less spaced out and more dense. That's going back the other way now. So the ice block is melting, the bonds break, the water molecules can fill in those big hexagonal empty spots and become more dense, and so the water becomes more dense overall, liquid water being more dense than ice. But as it starts to melt, it doesn't all instantly change from solid to liquid. What you get is you get water ice crystals still within the liquid water. And those water ice crystals are still going to have these big gaps in them that aren't filled in with liquid water because they can't get there because it's in the middle of the solid crystal of ice. And that means that the solid crystal, being less dense in the water it's floating in, is going to lower the density overall of the water. So the average density will be higher than it was for solid ice, but not as high as it is for water once all those crystals have melted. So for the first few degrees, from 0 degrees up to 4 degrees, there are still some of these ice crystals. Regardless of whether the water started as liquid and is getting cooled down to 2 degrees Celsius or some single digit Celsius, or it started as ice and is melting and hasn't quite finished melting. If it's in that range from 0 to 4 degrees Celsius as liquid water, then there will be some ice crystals. And those ice crystals will be less dense than liquid water, and therefore they will lower the average density of the water. So what we see is that 4 degrees Celsius water is the temperature at which all the ice crystals have gone away. They've all broken the bonds. We have no more crystals left. 4 degrees Celsius water is the densest that water can be. If you get any colder than 4 degrees, some of the ice crystals start forming again. The water gets less dense. It expands slightly. If you get warmer than 4 degrees Celsius, then we don't get any ice crystals forming, but now all the water molecules are getting a bit more of that translational kinetic energy. They're spreading out a little bit and the water starts expanding. So either way you go from 4 degrees Celsius, the water will start expanding. When you're exactly at 4 degrees Celsius, the water will be at its most dense. So from 0 to 4 degrees Celsius, this is just what I was saying. It gets more dense as it warms up from 0 to 4. It's getting more dense, which is the opposite from almost every other substance. Most substances will get less dense as they warm up. So that is an interesting one, water density. So I do recommend taking a bit of time to think about that and process that whole sort of change in water density between 0 and 4 and then up again from 4. If you get access, I think I've given you access to the 2020 semester 2 mid-semester tests. One of them had a question on water density, and that's a good little test in there to think about some of those properties. The next part of this lesson is talking about methods of heating. So as I said, we have defined heat. Heat is the flow of energy from one object into another, or one substance into another. How does that occur? How does that energy actually flow? That's what we're going to have a look at in this half of the lecture. When we've got two solids, we've got just lines of atoms that are all lined up. I already said lines, that's why I was trying to avoid saying lines again, but they're all lined up. They're in their lattice, in their crystal structure. You push it up against another one. Now you've got atoms from this substance bumping into atoms from this substance, and as they bump into it, the ones with more energy will lose energy to the ones with less energy. So the hot object, or the hotter object, it doesn't have to be hot, the hotter object will lose energy to the colder object. This is repeating ludicrous numbers of times because we've got so many of these tiny little atoms. Remember how small they are, how many there are in any object. So it's happening millions and billions and countless times. All these atoms are all losing a bit of energy to the neighbors in the cold object. And so the energy just slowly transfers from the hot object into the cold object. And the temperature of both objects changes until they reach thermal equilibrium, which, if you recall, was just meaning that the average temperature across both objects is the same. This is called conduction. So conduction is the transfer of heat by direct contact. So the atoms are literally bouncing into another object's atoms and providing the energy to them. So that is conduction. Conduction occurs not just between objects, but actually within objects. That is how an object can be heated in one place and the whole object heats up. If that didn't work, then when you tried to heat up a frying pan, just the very bottom of the frying pan that touches the element would get hot, and then none of the rest of the frying pan would get hot. So it would only be the very outside bottom layer that would be hot, and that would not be useful. The fact that the whole frying pan gets heated up, that is conduction at work. So conduction is the transfer of heat by atomic collision. For metals, a lot of us are aware that metals are good conductors of heat. That's because their outermost electrons become free electrons, which can move anywhere throughout the solid. We haven't really talked too much about electrons and free electrons and metals and things. But essentially, when the atoms of a metal bond together into that nice rigid structure that we've talked about when they form a solid, they lose a couple of electrons. It depends on which metal it is as to how many, and those electrons they lose are free to move anywhere throughout the metal. They're just shared by everything in the metal rather than being attached to a single atom. And so those electrons, because they're small and are free to move anywhere, they can take some of that kinetic energy and move all the way down the other end of the object and bounce into an atom down there and heat up that end of the object. Yeah, so electrons just help that conduction occur quicker. It still occurs without the electrons, but it occurs more quickly with the electrons. So for that reason, metals are the best thermal conductors. Insulators are just things which are not good thermal conductors. So if we have poor conductors, they are good insulators. A conductor and an insulator at the same temperature will have different effects on objects which come into contact with them because of how quickly they can facilitate the transfer of heat. If you have a good conductor and you push another object up against it, the good conductor will give that other object plenty of energy because it's a good conductor. If you have a good insulator and you push another object up against it, then that good insulator will not provide much energy to the other object. And so the other object will receive more energy from the good conductor than it will from the good insulator, even if the conductor and insulator are at the same temperature. And so it affects how well they can pass energy on to the object that they're in contact with. In general, liquids and gases are not good conductors. A lot of insulators are poor conductors because they contain spaces filled with gases, and gases are not good conductors. If you've seen windows have the best insulated windows actually have 2 panes of glass with gas in between, and that gas is a poor conductor so that the heat cannot be conducted through the glass and out into the atmosphere outside. If a liquid is a poor conductor though, then how come when we boil a pot of water, it heats all the water? It doesn't just heat the very bottom part of the water, it heats all of it. That comes back to our idea that we've already had of particles in liquid being free to move around. Remember that we said that heat is the average translational kinetic energy of a substance. If you heat the bottom of a pot of water, as per the diagram here, those molecules that get that energy, in this case I've coloured them orange, those molecules that I've coloured orange, they've got more energy, they're going to move a bit more faster than the other molecules, and because they're free to move anywhere, they will spread out and move around. And you'll also remember that as something heats up, it expands, it wants a bit more space. That makes it less dense. And what do we know about something that's less dense when it's submerged in a liquid? It floats. So even though we're talking about water molecules inside a pool of water, these hotter ones need a bit more space, and that makes them a little bit less dense. So they're going to rise to the top of this pool of water, in this case, a pot of water. And that will allow other cold water molecules to get to the bottom where they are now in contact with the hot surface of the pot, and they will get some energy, and then they will rise to the top doing the same thing. And so that process of the molecules heating up, rising, making way for more molecules which then heat up and rise and so on and repeating, that is called convection. So convection is heat transfer through fluid flow. So the heat moves from the bottom, the energy moves from the bottom of the pot to the top of the pot. So we've got heat because we've got energy moving, we've got energy flowing from the bottom to the top, but it's still staying in that one same particle. That one molecule still has that energy. So it hasn't given it to another molecule, but it's spread it throughout the substance because the substance itself has moved its parts around. Obviously, the molecules in the water are getting their energy from conduction because the pot surface is providing that energy to the water. So that is conduction. And then the water flow, once it gets the energy, that's the convection. You're probably familiar with the phrase hot air rises, and that is exactly the idea of convection. The idea that as you heat up a pocket of air, it now becomes less dense than the surrounding air because gases do technically expand. As I said, we're not going to get into all the equations and formula for thermal expansion for gases, but they do still try and expand. They want a bit more space, and so that rises much the same as you see here with liquid convection. There is a little question, though, that often rises about air and heat, hot air rising. If hot air rises, how come the upper atmosphere is colder, right? As air rises, as it goes higher up the atmosphere, remember that the atmosphere becomes less dense. So at some point, the density of air moving upwards will match the density of the air around it, and it will stop moving upwards. But that doesn't explain why it's colder. It explains why it's not permanently moving upwards, but it doesn't explain why it's not colder, why it's colder up there instead of hotter. And the answer is that it does work to expand. This isn't something I'm expecting you to remember or memorize, but it is a useful concept to be aware of. As the air travels upwards, it does work because it pushes other air out of the way in order to expand and take up a bit more space. So the warmer air is doing work on the surrounding air, and work is just energy. Temperature is energy, therefore it's losing energy, therefore it's losing temperature. So warmer air cools it as it expands, but because it is doing work, but even though it's lost some energy, because it's risen, it's still warmer than the surrounding air, so it will keep rising, and it'll keep doing that until it runs out of its energy and becomes thermally equilibrated with the surrounding atmosphere. We've looked at convection and conduction now. They both required physical matter to transfer heat. For convection, the atoms themselves were moving around. For conduction, the atoms were passing along their energy through collisions with other atoms. But the sun is nowhere near Earth, and the sun is how we get all our energy. So how does energy from the sun arrive at the Earth, even though there is no matter in space for it to conduct or convect through? How does that happen? There must be some form of heat transfer that doesn't require physical matter, and that form of heat transfer is radiation. So little packets of pure energy called photons are known as electromagnetic radiation or light. We're not going to go too much into this right now. This is in fact the topic of our last section where we look at light. We look at waves and then we turn that into light. But for now, what we do want to be aware of is the idea of these things called photons. So photons are what makes up visible light. And there are other forms of light as well. Visible light is the colors we can see, but things like radio waves, X-rays, and other gamma rays and all sorts, they are all light as well. They're just not visible light. Now, as I said, we'll come back and we'll look at this area in more detail. For now, we want to know that photons exist, and the energy being transferred by these photons we call radiation. So the photon is emitted by the sun, and it's just a little packet of pure energy. There's no matter with it. There's no atoms or electrons or anything. It's just energy. And that little packet of energy is released by the sun, travels through space. Some of them hit Earth, only a very small amount of them because the sun is emitting them in every possible direction at all times, and we're one tiny little speck really far away, so we're getting a tiny, tiny fraction of all the photons emitted by the sun. But when they do hit the Earth, that is pure energy hitting the Earth. And so that's how we get energy from the sun. So these photons do not need any kind of material to transfer through. So convection and conduction both needed matter. They both needed atoms in some form or other, but radiation does not, because it is just pure energy flying through space. Every single object is actually emitting this radiation energy. Everything. Every single object. If it's above absolute zero, it's emitting radiation. So we will release photons, particles of light. They are not visible light all the time, but everything that is above absolute zero is releasing particles, releasing photons of light. Particles of light, I apologize by saying particles. I'm probably going to confuse everyone when I just said there's no matter in them. Photons are what we call the particle form of light, but it doesn't mean there's any mass. They're still just pure little packets of energy. So as I said right there, theoretically something at absolute zero wouldn't release any. As soon as it's got any kind of thermal energy, it will be releasing some of these photons. The sun is fairly hot, so it emits a lot of them, and light has no problem traveling through the vacuum of space, so it gets to Earth, and radiation is therefore how we receive energy from the sun. In the textbook at this point, it talks about frequency, wavelength, and radiation curves. If you are following through the textbook, don't worry about this section for now. I will come back to this section after we have talked about light and after we've talked about waves, and once we understand what frequency and wavelengths and radiation curves all actually mean. The textbook, I just feel, was a little ambitious trying to introduce this now when you haven't actually met those concepts yet. So I will leave all of that until the last section of the course. Just to really drill home what I said, everything is constantly radiating energy. Any matter that has any thermal energy, anything at all, so anything above absolute zero, which is literally everything in the universe, everything is emitting some of its energy as heat, as radiation, as thermal radiation. So everything is always radiating. Everything in this photo is radiating thermal energy. Literally everything. I could have used a photo of anything, anywhere. And I can't say this too many times. Everything is radiating energy always. It's just a fact. It's just a statement. You memorize it. That is true. Everything is always radiating energy. So where does this energy go? If everything is always radiating this energy, these little packets of thermal energy flying about everywhere, where do they all go? They fly about until they're hit by some other piece of matter and get absorbed. So what's absorbing all this thermal energy then? Everything. Everything is also absorbing thermal energy constantly. So everything in the universe, everything is emitting thermal radiation and absorbing thermal radiation. Some emit a lot more, like the sun, it emits a lot more than it receives. Others receive more than they emit. The Earth as a whole receives more than it emits, and that's why it's warmer than the space temperature around outside it, which is right down at a few Kelvin. So everything is constantly absorbing and constantly emitting. Here on Earth, everything is constantly absorbing some radiation energy. I'm absorbing radiation energy right now, but I'm also emitting radiation energy. So if everything is emitting radiation and everything is absorbing radiation, that explains why we don't run out of energy. Because you might have thought when I said everything is constantly giving away this energy, giving away its thermal energy, then why don't we all run out of energy and end up at absolute zero? It's because we're constantly absorbing energy too. So there's this nice balance, this equilibrium of absorbing energy and giving out energy that means we always have some thermal energy. If something is better at emitting radiation, it's better at giving it off, it gives away more energy, then it turns out that those same things are good at absorbing radiation. So things that are better at giving off radiation are also better at absorbing it. So the internal energy of most objects don't change because the radiation is emitted and absorbed at about equal rates. So something that's just sitting there in the middle of your room, choose anything that's not straight out of a fridge or out of an oven, choose anything that's just sitting there like a book or a table. It's absorbing radiation, but it's also emitting radiation, so its temperature stays pretty constant. Since different materials can absorb different amounts of radiant energy, even though they're subject to the same amount of radiation, what happens to the rest of the radiation? It's reflected. So if you shine radiant energy, which is just light, this could be visible light or it could be light that we can't see, like ultraviolet radiation or infrared radiation. If you shine radiation onto a surface, some of it is absorbed and some of it is reflected, bounces off the surface. The amount that's absorbed is determined by what the material is, and something that is good at absorbing will therefore be a poor reflector because it absorbs lots of it and doesn't let much bounce off, whereas something that is good at reflecting it, that bounces most of that radiation off its surface, is therefore not going to be able to absorb much, because again, energy conservation means that we must have the total amount of energy, the amount arriving at the surface, being the same as the amount that is left after. So that's the amount that reflects off the surface and the amount that's absorbed by the object. So if one of those is big, then the other one must be small, just by energy conservation. If something absorbs more radiant energy than it emits, then it is a net absorber. If it is overall gaining, that means it is overall gaining energy, so it will increase in temperature. If something is emitting more radiant energy than it absorbs, then it is a net emitter. And that means it is losing energy, it's giving out more than it's getting in, so it will decrease in temperature. We already know that heat flows from a hot object to a cold one, so that tells us that a hot object, anything that, by hot I mean anything hotter than its environment, must be a net emitter. Right? It must be a net emitter because heat is going to flow from the hot thing to the cold thing. Energy, radiation will hit the hot thing and it will absorb some, but it will be giving off more because it is hotter. So overall it will lose energy, it will cool down, and it will end up at the same temperature as its environment. A cold object, like a drink with ice in it, is going to be absorbing more energy than it is emitting, and so it will be a net absorber and it will increase in temperature until again it reaches the same temperature as its environment. So in general, things are going to come to the same temperature as their environment. That's why we have things like fridges and freezers. We make an environment that is permanently colder than the surrounding, the outside environment, the room temperature. And then when we put an object into that fridge, it will come to equilibrium with that environment, with the fridge environment, and therefore it will come down to the temperature of the fridge. Newton's law of cooling is actually a really simple law. It's almost common sense. The bigger the difference in temperature between two objects, the faster the rate of change of temperature. That is, the rate of cooling is proportional to delta T. That's all the law is. We're not going to go into heaps of detail on it, but it just means that the bigger the temperature difference, the greater that change in temperature is going to be. The change in temperature of the two objects is going to be. So if it was an object so say you've got room temperature and you've got two objects, one is a hot object at 100 degrees Celsius, one is a hot object at 50 degrees Celsius, and the room is at 20, then the one at 100 is going to have a greater rate of cooling. It's going to cool down more quickly than the one at 50. The one at 50 will still reach room temperature first because it's starting closer, but the one at 100 will give off more energy per second than the one at 50 will initially. Right, so the Newton's law of cooling is about the rate of energy transfer. It's not about how long it takes to get from its initial temperature to its final temperature. It's just about the rate at which that temperature is given off at a given temperature difference. As I mentioned, the sun is where we get our energy, and it is actually the primary source of energy here on Earth. Without the sun, the Earth's atmosphere would be very cold, somewhere between 2 and 100 Kelvin. That's a very big range, I agree, but regardless, they're all very cold because it's negative 271 and negative 173 Celsius. So it's somewhere in that range. It depends on other factors that is very hard for us to predict and actually know with any confidence what the temperature would be, but it would be somewhere in that very cold region. So the sun is providing all the energy that enables us and life on Earth to exist. The sun shines on one side of Earth at all times, only ever one side, because one side is facing away from the Earth, from the sun. And it provides energy in the form of photons. Those photons are absorbed by the atmosphere. Some of them are absorbed by the atmosphere. Some of them travel through the atmosphere and collide with things on the Earth's surface, like plants and the ground. The plants that receive this thermal energy in the form of visible light radiation, they absorb the energy and they make special use of it and turn it into stored energy. So they store it in their cells, and animals, including humans, consume those plants and then take that energy and convert it into their own energy stores, which they can then use to power their internal organs and muscles and other things. When the sun goes down and it's nighttime, the Earth isn't getting any sunlight, or that side of the Earth. The other side obviously still is, but the night side of the Earth isn't getting any sunlight. The atmosphere starts to cool down. But the objects are still warmer from absorbing radiation throughout the day, so that means that most objects are actually net emitters at night. They got warmed up by the sun during the day, nighttime comes, the atmosphere cools down, and now the objects are warmer than the atmosphere, so they emit energy, so they become net emitters. If an object is in contact with the ground, then it will experience conduction as well. It's still emitting radiation because everything is constantly emitting and absorbing radiation, so it's still emitting radiation. But if it's in contact with the ground, then it's going to be experiencing conduction as well. If the object is a good conductor, like metal, stone, or concrete, then it will receive energy from the ground. And the ground was also warmed up by the sun all day. So the ground has a lot of energy because the ground's huge, right? So the ground will be providing energy, and it will allow the object to come into thermal equilibrium with the environment, so including the surrounding air. But if the object is a poor conductor, it won't receive much energy from the ground. It can actually then continue to emit radiation until it's colder than the surrounding air. Remember that air is a poor conductor, so we're relying on radiation for this to happen. And at night, there's not much radiation going on because there's no photons coming in from the sun. So that means these objects, they can't get energy from conduction from the ground, but they're still emitting energy into the atmosphere because they are cold and there's not much incoming radiation for them. So that means they actually end up colder than the surrounding environment. They radiate all their energy away and they're not receiving much. So that means that we can get things that form a frost even though the air temperature never went below freezing. So wood, straw, grass, anything that's a poor conductor can cause a frost even if the air never actually dropped below freezing. The sun provides a lot of energy because it's very large. It travels away from the sun in all directions through space. I'm just looking at the slide and I'm realizing the text is very small, so I apologize for that. But anyway, the energy from the sun travels through all of space in all directions at once. I mentioned this already. It's going in all directions and the Earth is really tiny and we're far off and we absorb a tiny fraction of that. The solar constant is the name we give to the amount of energy from the sun that reaches Earth at all. So as I said, most of it's going in other directions, only a tiny bit is heading towards Earth. That tiny bit that does reach Earth is around about 1400 joules per square meter per second. All right, so 1400 joules per square meter per second. Joules per second is watts, it's power. So we can also say that as 1.4 kilowatts per square meter. Some of that radiation, as I said, is absorbed by the atmosphere. By the time we get down to sea level, about 1 kilowatt per square meter makes it through the atmosphere. So about 400 watts per square meter is absorbed by the atmosphere as it travels from the outer edges of our atmosphere towards the Earth's surface. About 400 watts is absorbed by the atmosphere in that distance. And then when we reach Earth's surface, we've got around about a kilowatt per square meter to be received. But that's only for the bit of Earth that is facing the sun directly. Right? That's for the bit that's facing the sun directly. The bit of Earth that's not facing the sun directly, so the sunlight's coming this way, but the Earth is at an angle, that's not going to receive as much per square meter, because 1 square meter on this slope is not going to be seeing a whole square meter of the sunlight, if that makes sense. I'll expand a little bit more. So that means that as you move away from the point that's directly facing the sun, you actually end up getting less energy per square meter, but still a decent amount. By the time you get to the exact perpendicular to the sunlight, which is dawn or dusk, the exact top or bottom of the Earth relative to where the sun is, you're getting no sunlight, and then for the whole night you get none until you're back to dawn again, and then you start getting more up till that midday where you get the most. Right, so that's what happens. Since so much energy is being received from the sun throughout the day, it makes sense to try and collect some of it, and that's what solar power systems are doing. They're trying to collect that incoming sunlight and use it to heat our homes, power our appliances, and so on. If the entire solar energy hitting the surface of a house could be captured, then for an average house, it would actually provide around about double their typical electricity usage. Of course, we can't capture it all perfectly, but we can capture it pretty well. So we could very easily have an entire society which was entirely based on solar panel power collection. But of course, we have other methods as well with our wind turbines and things. But as I promised, I want to take a second to talk about that sunlight hitting us at different angles. So I said that when you've got the Earth and you've got sunlight, sunlight is coming in. Sunlight is pretty much parallel because the sun's so big and so far away that the sunlight is pretty much always parallel like this. If you are sitting right on the point of the Earth that is directly facing the sun, then 1 square meter of area here is going to catch exactly 1 square meter of sunlight. But if you are sitting down here, then your 1 square meter is not going to catch 1 square meter because it is now a smaller area as seen by the sun. Right? So just to demonstrate this, and hopefully this will work. I'm just going to stop my share, come back to my video camera. Right, so if I have this as my square meter, which is not square nor is it a meter, but if this is my square meter and I'm facing the sun directly, then all of this will catch sunlight. Right, that will all catch sunlight. But if I'm further down the Earth, then it will look like this, and it now no longer looks like quite as big an area, and so you're going to be catching less of that sunlight. And so that's the whole idea behind it. As you tilt away from the sun, you're catching less sunlight because the sunlight is still always traveling directly away from the sun. Sometimes we want to stop heat transfer. Sometimes we don't want heat transfer to occur. We might make something really cold. We might make a nice cold beverage and we want it to stay cold. How do we stop heat transfer from occurring? We need to think about each of the 3 types of heat transfer and think about ways we can prevent it. Conduction and convection both involve matter. So if we get rid of matter, that would be easy, but getting rid of matter is not that simple. But for conduction, we could use an insulator because an insulator is not good at passing energy by conduction. So an insulator would stop that method of heat transfer. For convection, we could provide no path for fluid flow. So we could use solid objects, or if we have to have liquids, we could have some way to prevent flow. So we could have liquids in separate little sections, not one big body where it can flow. For radiation, For radiation, the matter itself doesn't matter because radiation is just little energy packets that fly through space. They don't need any matter. So what we would need to use is some kind of poor emitter so that the object can't emit any energy. The vacuum flask is actually a great example of these three methods of heat transfer and how we can combat them. Because what they have is a vacuum space. Now, I said in a previous lesson that vacuums are very hard to create, and that is true, but it doesn't even need to be a perfect vacuum. Just a partial vacuum is actually going to be pretty good because a partial vacuum will severely limit the amount of matter that's in there to conduct and convect that energy across. So if you look at this diagram of a vacuum flask, you can hopefully see this sort of black, dark, hollow region. The main central chamber is where you put the substance you want to keep hot or cold. And then right on the other side of that wall, you'll see this dark area, and that is the vacuum area. That is the vacuum, so it's a completely sealed vacuum, and it's got no matter at all in it, or as I said, realistically, it'll be a partial vacuum. It'll have some matter, but not as much as the general atmosphere. And because it's a partial vacuum, that means that you're reducing conduction and you're reducing convection so that you will get very little heat loss through those two methods. The other problem is the radiation. And so what you want is a poor emitter. And remember that poor emitters are also good reflectors, right? Poor emitters, poor absorbers are the same thing, poor emitter, poor absorber, but that means it must be a good reflector because energy conservation says the energy that hits it has to go somewhere. If it's not being absorbed, it must be being reflected. So get a reflective surface like a silvered surface, like a mirror, and use that to make your vacuum canister. And then any energy that does get reflected, does get emitted, will just get reflected back off the silver and go back into the material that it came from, the soup or the iced cold drink. So a vacuum flask, if properly made, can combat all three types of heat transfer as much as possible. Obviously, you still need an opening. You still need a way to get the substance in or out of the flask, otherwise it would be no use. So you still need some kind of stopper, and that stopper obviously is not going to be completely a vacuum. Even if it had a partial vacuum in it, it would still have some solid areas where stuff could get out. So you often make that out of some kind of plastic or insulator in order to prevent that conduction. So a vacuum flask is a really good thing to remember when you're thinking about those three types of heat transfer, because it A, reminds you how we can stop them all, which will help you keep in mind how they all occur in the first place, and it also incorporates all three: conduction, convection, and radiation. So that's the end of this lesson. As I said, there were sort of two parts to it. One was talking about thermal expansion and the other was talking about heat transfer with a few other bits and pieces in between.